So last week was all about mechanics. We learned some very useful new skills. Today, and this week and the next, we're going to change gears. And whereas last week was very practical, very earthy, this week it's going to start becoming a little bit more theoretical, as well as next week, as we delve with great depth into one of the most exciting algorithms. If you can call an algorithm beautiful, this would be beautiful. So we will delve with great depth into AdaBoost, see how its internals work, see why it works and why we would want to use it. So before we get into AdaBoost, before we get into this whole sphere of ensemble-based machine learning, I think it's important that we recap a little bit in terms of what we have learned in 158.222, in terms of some of the algorithms that we covered, so that we can contextualize the material that we're going to cover this week and the next. So you might remember in your material from 222 that there are, roughly speaking, two main families of machine learning algorithms. You have parameterized, parametric machine learning algorithms, and you have non-parametric machine learning algorithms. Now, we covered one of each. So when we talk about parametric machine learning algorithms, what we talk about is algorithms like naive Bayes, right? You all remember naive Bayes and how it works? Now, parametric algorithms are called that because they have a very fixed set of parameters that are used to describe a data set from which they're trying to pull information out of a pattern. So if we go back to the naive Bayes algorithm, it's really simple because all we're talking about is for every class and for every feature, we figure out what the mean is, what the standard deviation is, and what the prior is. Those are the three things that we need. No matter how large or how small your data set is, those are the only things that you can pull out of the data set. So you can have 1 million samples or you can have 10 billion samples. Your classifier will be the same size, fixed size. That's a parametric machine learning algorithm. Those algorithms are really nice. They're nice because A, they're simple. They tend to work pretty well. The accuracy is not bad. Usually it is enough. They work really well with smaller data sets. And because they're simple algorithms producing a simple classifier, they tend not to overfit. The weakness of these kinds of algorithms is when the data set becomes or is complex, when the decision boundary is by far more complicated than would be required or able to separate with a linear function, that's when they fail. So more often than not in the real world, we are coming across data sets that are more complex and that require solutions that are more sophisticated than the ones that parametric machine learning algorithms offer. So then we come to the non-parametric machine learning algorithms. Believe it or not, you covered already one of them in 222. The funny thing is, unintuitively, K nearest neighbor is a non-parametric machine learning algorithm. Because if you think about K and N, it requires the data set, right? It doesn't work without the data set. So as your data set grows, it kind of grows in terms of its parameters because the entire data set is its parameters. So it's a non-parametric machine learning algorithm, but it's an unusual one. So what we're now going to cover is one that I would say is at its very, very core and at its very, very heart, a non-parametric machine learning algorithm. That means this algorithm is going to produce a classifier that will grow, potentially infinitely if you want, in respect to the data set. You can make this classify as complex as you like, which means that no matter how complex the decision boundary is between all the classes that you're trying to separate, it can find a mapping. It can find the mapping, whereas the parametric machine learning algorithms will fail. Now, the downside to non-parametric machine learning algorithms is they tend to overfit. They are more complex, which means they are more opaque, harder to understand. But the biggest thing, the biggest challenge is they tend to overfit, particularly if you don't give them enough data. If you give them small data sets, they'll overfit grossly. So because overfitting is an occupational hazard when it comes to using machine learning, it's such a big challenge that is always with us. Machine learning specialists have come up with a new solution, a new way to handle complexity in such a way that you can mitigate and lessen the probability of you overfitting your data set and producing a classifier that does not generalize. And here's where we enter ensemble-based machine learning. This is the heart of ensemble-based machine learning. This is what it assumes. It says, what if you had a really complicated problem, instead of trying to produce a really complex function classifier that separates all the classes, what if you just don't try that hard? What if you just try and produce an okay solution? One that is roughly correct most of the time, but usually wrong. Okay? A solution that is just roughly, or just better than chance, let's say. And what if you created many of these rough rules of thumb, these rough solutions? Is there a way that we can put them all together and as an ensemble produce a classifier that is sophisticated and complex enough to find that decision boundary that separates the classes? That's the heart of ensemble-based machine learning. And this is a very powerful idea because sometimes when you have a really complex data set, computationally you can't actually find that very, very complex function in a multidimensional space. Sometimes you don't have the computational resources. So if you can break the problem down into these very attainable goals, where you're not trying to do things perfectly, you're just trying to do an okay job, and you do that enough times and put that together, and voila, you have an amazing solution. That's what it tries to do. That's ensemble-based machine learning. Ensemble-based machine learning works really well, not just on these super complex problems with very difficult decision boundaries, but it works on really large data sets. So the idea is you can take a massive data set and take one classifier and learn on this subset, learn another classifier on this subset, learn another classifier on this subset, and then kind of put it all together and you've learned the entire data set, but you have parallelized the whole problem. This is where ensemble-based machine learning comes in very, very handy, particularly in the age of big data. So here's a challenge. When you create your ensemble-based solutions, what we need to ensure is when we create each, and we call them, this is the term for it, we have one strong classifier which is composed of lots of weak classifiers. How can we ensure that each weak classifier focuses on a particular subspace of the data set so that each one learns a particular part of the problem, this one whole big problem? And secondly, how can we emphasize and give greater weight to classifiers, to weak classifiers that have more competence than the others? Is there a way of amplifying certain weak classifiers that are better than the others? And then lastly, okay, so we have a whole suite, an ensemble of these weak classifiers. How can we intelligently put them together so that those that are experts, they're amplified in their ability to vote when it comes to classification time, to run time? And how can we cancel out those ones that are a little bit weaker? Their misclassifications, can we somehow cancel them out? That's where boosting comes in. And boosting encapsulates all those challenges, all those ideas that are quite profound. And in a way, they're not that new, right? Because we do this all the time. You and I, we all do this. When there's a difficult decision for us to make, something that is critical, usually a health decision, you don't consult just one doctor, do you? For something really important, you go to several doctors. Not that you devalue some of them, but you seek multiple opinions. And each doctor will have a slightly different perspective, slightly different set of experiences, and will tell you something that is maybe slightly different. And you collate all those things together, and then you formulate your final decision.